Let's do some homework problems together. See what kind of surprises I've gotten for myself this time. We'll start with some completing the square ones since it may be unfamiliar with some of you. 2x squared minus 8x plus 3. So to complete the square here, we need a coefficient of x squared to be 1. We're going to start by factoring out a 1/2. That's the same as multiplying the insides. Sorry, we're factoring it out by 2, which is the same as multiplying the insides by 1/2. You can check your answer by distributing. And now we look at our b. Our b is -4. And then we need to add b over 2 squared. So b over 2 is -2. b over 2 squared is +4. So we need a 4 right here. What we're going to do is add a 4. And if we add a 4, we have to also subtract a 4. Now we have two pieces. This is a perfect square, and this is our leftovers. So it's 2 times x minus 2 squared. It's no coincidence, by the way. This will always be b over 2. And then what's the blue stuff? -8/2 plus 3/2 is -5/2. So now we distribute that 2 and we get 2 times x minus 2 squared minus 5. That's completing the square. That will be useful in the homework problems. You can check your answers by multiplying this all out, and hopefully it equals what we started with. So let's do 145 with that in mind. Wait, I don't think we have to complete the square in 145. One of these I have you complete the squares. 145 is the square root of x to the 6th minus x to the 8th. Right off the bat, let's rewrite this. Let's factor out an x to the 6th. Okay. That gives us the square root of x to the 6th, which is the absolute value of x cubed. We factor out an x to the 6th, we're left with 1 minus x squared left over. Oh, this is really similar to that one I did in the last video. In fact, it's almost the same. The difference is that there's an x squared, or an absolute value. So it's basically going to be the positive when x is positive, and the negative when x is negative. Yeah, it's actually pretty tedious. I don't think the book probably even worries about it that much. But let's do it. No, let's not do this problem. It's too similar to the other one. I wanted to do something new. I don't think the absolute value is enough to redo so much. Let's do maybe maybe 143. Integral of theta cubed. Why are they using thetas here? I'm changing it. We can call the variables whatever we want. Dx over the square root of 9 minus x squared. We should express our final answer in the variable that they want. But we can do our work, whatever variable we want. Yeah, actually, I know I'm very wishy-washy today. We'll use thetas. I want to show you what it looks like if we use thetas. We'll just have a new variable. Okay. So, can we use a u substitution? Maybe. Maybe we can. Let's try it. If u is 9 minus theta squared, du is -2 theta d theta. So d theta is -1/2 theta du. So that's going to be theta cubed. Let's not worry about that yet. Square root of u times dx. Sorry. times d theta, which is negative 1 over 2 theta du. One of the thetas cancels, which gives us a theta squared. And theta squared is 9 minus u. The negative a half comes out in front. This becomes 9 minus u over the square root of u. Is this better or is this not better? It's better. Because look at that inside. Split up the fraction. This is 9 u to the negative a half minus u to the positive a half. We don't even have to use a trig sub here. And whenever we can avoid a trig sub, we avoid a trig sub. The negative 1/2. Add an exponent, divide by that exponent. Add an exponent, divide by that exponent. And u is 9 minus theta squared. I'm going to try to not skip steps here. 9 minus theta squared minus 2/3. 9 minus theta squared to the 3/2. Oh, did I drop one of my plus c's at the end? I did. There's a plus c right there. There's a plus c right there. There's a plus c on this one. I lost all my plus c's. Negative points. So again, we could distribute this negative a half. We get negative square root of 9 minus theta squared plus 1/3. 9 minus theta squared to the 3/2. And we could simplify this just like I simplified it in that last, in 3.3.6 as well. But you don't really have to. I'll take this as a final answer. All right, 161. I know one of these, I do some complete the square fun for you. Yeah, there we go. Integral of 1 over x squared plus 2x plus 1. Oh, let's not do this one. Let's do 163 instead. That's harder. I want to do something harder. 1 over the square root of negative x squared plus 10x. All right, Desmos, or my OpenStax, you're going to do this to me, huh? Negative x squared plus 10x dx. All right, so we didn't really do any of these in the videos, but we're doing one now. Can't use a u sub. Can't use integration by parts. We can't set up a trig sub. We need to complete the square, which is a little extra fun because there's a negative. Okay. So a couple of ways going about this. Let's go off to the side. Say negative x squared plus 10x is equal to negative x squared minus 10x. And we want to complete the square. So b is 10, or negative 10. Half of that's negative 5. Square it's 25. So we need to add a 25. And if we add a 25, we need to subtract the 25. And that gives us negative x minus 5 squared minus 25, which is 25 minus x minus 5 squared. So this becomes the integral of 1 over the square root of 25 minus x minus 5 squared dx. So why is this completing the square useful? It's because this is the form this is basically the form 1 minus cosine squared, 1 minus sine squared, whatever you want to use. So we want x minus 5 squared. We want that to be 25 sine of theta. Because if it were 25 sine of theta, we could do a trig sub. So what is x going to be? I got no clue. So, well, I actually haven't done one of these in a long, long time. So we can take the derivative of both sides with respect to x. Is that what we want to do, maybe? Let's try it. We don't want to FOIL this out. Oh, yeah, let's see. If we take the derivative of both sides with respect to x, we get 2 times x minus 5 times the derivative of the inside, which is 1. The right-hand side is 25 cosine of theta d theta. Okay. Still not seeing how this is going to be nice. So dx is going to be 25 cosine of theta d theta over 2 times x minus 5. Oh, and we know what x minus 5 is. We don't know what x is, not easily, but we do know what x minus 5 is, right? So this is 25 cosine of theta d theta. X minus 5 is the square root of this. So it's 5 times the square root of sine of theta. Okay. Okay. It's 2 times 5. That's not a 25. That would be a bad mistake. But we do get some cancellation, right? I'm going to write this in a lazy way. It's 5 halves now. So what do we got? The square root of 1 over 25. We said that whole perfect square, 25 sine squared, times dx, which is 5 cosine of theta, d theta, all over 2 square root of sine theta. This one's not going to be as bad as it looks, I think. Let's see if I'm wrong. So let's simplify that square root off to the side. All right, the square root of 25 minus 25 sine squared theta. Just 5 times the square root of cosine squared of theta. Just 5 absolute value of cosine of theta. And what does our domain and range look like? Ooh, that's maybe a little harder. The x can be anything, but x squared minus 5 is always positive. All right, the smallest this can be is 0. And the biggest this can be is infinity. Maybe that's maybe a problem. Oh, no. That's not true. That's not true. We have to look at maybe the radicand. This guy over here. What is x? We need x squared, negative x squared plus 10x. We need this to be strictly positive. If it's 0, we divide by 0. And if it's negative, then we have the square root of a negative number. And this is kind of hard to do. Factor out an x. We need this to be positive. So these are kind of tricky to do. One of the ways is, since this is a continuous function, you know, something will happen when x is 0 and something will happen when x is 10. You just plug in some points. If x is to the left of 0, if x is negative 1, we have a negative times a positive, it's a negative. If x is like 5, positive times a positive. And if x is 11, negative times 11. So we need this to be true. So we know that x is between 0 and 10 exclusive. So if x is between 0 and 10, what does that tell us about sine? If x is 0, this is 25. If x is 10, it's also 25. So the max it can be is 25. What's the minimum it can be? So between 0 and 10, what's the minimum of this parabola? Well, that'll be easier if you kind of graph it. I'm sure some of you might be able to do it more quickly. Right, x minus 5 squared. That's the parabola shifted right 5 units. The smallest it ever gets is 0. Oh, that was maybe obvious. That was probably obvious. The smallest it ever gets is 0. So that means sine is between 0 and 1. If sine's positive, then we're good to go. The sine's between 0 and 1. That specifically means that theta will be in the interval from 0 to pi over 2. First quadrant. Oh, sorry. Exclusive. First quadrant means that we did this for a reason. Where did I write that reason down? First quadrant means that cosine's positive. All right. Always got to know. So this becomes the integral of 5 cosine of theta d theta over that square root. We said that square root is 5 cosine of theta. And there's still a 2 for the sine theta down here. Oh, this is nice. Beautiful. Wait, I don't know if it is beautiful. Wait, this might be terrible. This is 1/2 integral of 1 over the square root of sine of theta d theta. Do we know how to do this? I don't know how to do this. Maybe integration by parts. Huh. Try integration by parts. No clue. Okay, I actually thought about cropping this out, cutting this out from the video, but I decided to leave it in because I really want to emphasize something that I even fell prey to here. This, by the way, this is really an interesting integral. I did some research on this integral. Yeah, we're not going to talk about this one. We're not going to do it. Okay. Don't use trig subs if you don't have to. All right. This was a kind of a cool little setup of trig subs and some cool applications. But at the end of the day, it reaffirms the point that you're not supposed to be doing that here. But do we actually have? Watch this. What if u is equal to x minus 5? Just x minus 5. Then du is dx. We get the integral of 1 over the square root of 25 minus u squared du. Oh, let's adjust this a little bit, actually. Let's let u be 5 times that. The du is 5 dx. So we need a 5, so we're going to divide by 1/5. And this will now be... all right, hold on. Let's not do things. Let me reset. Okay, so let us let 5u equal to x minus 5. Right? That's going to be nice because then x minus 5 squared is going to be 25 u squared, like so. Let's let u be 1/5 x minus 1. Du is 1/5 dx. We'll have a 5 out here and turn that into a du. And then what do we get? We can factor out a square root of 25 on the bottom, which is 1/5. They'll cancel out. We get 1 over the square root of 1 minus u squared du, which is just arcsine. Don't use inverse trig if you don't have to. This is arcsine of u, which is 1/5 x minus 1 plus c. Okay? And if you check your answer with the book, this is 163, 1/5 x minus 1 plus c. That is what indeed the book has. Okay, so yeah, let that be a lesson. I am intentionally leaving that in when I could have taken it all out. Yeah, because I think it's interesting. And yeah, I make mistakes too. So that was not 161, that was 163. 169 is the next one I wanted to do. The book sometimes moves things around. Evaluate this integral using the form 1 over u. And then use arctan, or use a tangent sub, to do this two ways and compare them. The integral of x over x squared plus 1 dx. We're first going to do a u substitution. I'm going to blaze through the u sub really quickly because that's nothing really new or interesting. Okay, so if we do that, we need a 2, so we have a 1/2. We get 1/2 the integral of just 1 over u du. 1/2 the natural log of the absolute value of u. Absolute values are unnecessary. And this is the first method. I'll go through the second method more slowly. So the second method would be to let x equal tangent of theta. And then dx is secant squared of theta d theta. And then our integral becomes the integral of x over x squared plus 1 dx, which is secant squared of theta d theta. Our denominator is just secant squared of theta. And we get some really nice cancellation. We're left with the antiderivative of tangent of theta. Let's keep this on the same page just to make things a little easier. And the antiderivative of tangent is, you do a u substitution. I think it's the natural log of the absolute value of secant of x plus secant of theta. And what is secant of theta? Well, we'd go off to the side and say, okay, x is tangent of theta. What's secant of theta? Well, do we know what quadrant we're in? Yep, just like before. Theta is between negative pi over 2 to pi over 2. Oh, maybe we don't know. We're either in the first or the fourth quadrant. But cosine's positive in first and fourth quadrant, so it doesn't matter. So if this is some theta, tangent is opposite over adjacent. This will be square root of 1 plus x squared, or x squared plus 1 if we want to be consistent. So we're looking for the secant of this. Well, secant is a reciprocal of cosine. So the secant will be square root of 1 plus x squared. Is this the same? It's close. Remember your properties of natural logs. An exponent can come out in front. The exponent is 1/2. We don't need the absolute values since it's always positive. We can write x squared plus 1 as 1 plus x squared. Hey, they are the same. These are the same. Woohoo. No problem. Next problem. Last one. 177. Solve the initial value problem. Again, we haven't talked about these too much, but they are fun, so I'll talk about it here. dy dx. This is just a simple version of a differential equation. Y of 0 equals 3. This is using function notation, just like f of 0. Y is a function of x. So let's solve for dy dx. If we can get dy dx by itself, and we only have x's on the other side, we're good. Fun fact, if there's a y, we can solve that too. Just a little differently. Then we need everything with y's and dy's on one side, and x's and dx's on one side. And that's another technique for like basic differential equations. And then that won't always work either. And then you can get some really wacky ones. Anyway, for this one, just get dy dx by itself. Because If two functions are equal to each other, there we can integrate both of them. All right. And actually, if we really want to be specific, hey, yeah, we actually should do it this way, huh? So move the dx over to the other side and then integrate both sides. Left-hand side will just be y plus a constant. And the right-hand side will also be plus a constant. So let's deal with the constant later. Look at the integral, 1 over. I don't need to just write it again. We will use a trig sub because I'm pretty sure we have to this time. Pretty sure we have to. So what form is this? This is the form 1 minus sine squared is cosine squared. We'll let x be 8 sine of theta. So x squared has that 64. Dx will be 8 cosine of theta, d theta. So this becomes 1 over. I'm really doubting myself. Do we need a trig sub here? I'm just going to do it apparently. I think we do. 64 minus 64 sine squared of theta times 8 cosine of theta d theta. If we don't, we'll find out. So we get an 8 that comes out. We get a 64 that comes out. That leaves us with cosine of theta d theta all over 1 minus sine squared, just cosine squared. So cosine over cosine is 1 over cosine, which is secant. And we know what secant, the antiderivative of secant is. The natural log of absolute secant theta plus tangent theta. And this is all equal to y. And again, remember that y of 0 is equal to 3. We'll need that later. And now we just need what x is, or what secant and tangent are. Remember that x is sine of theta. No, that x is sine of theta, and specifically here, do we know the domain of x? X is going to be anything except for 8. All right, so this integral is possible to do without a trig sub, but it uses inverse hyperbolic tangent, which we're not covering the hyperbolic functions in this class. So that's how you do the general integral. We can do the integral if x is between -8 and 8 with a trig sub. So that's what we're going to do here. Okay, so if we have this, again, x will, so theta is going to be either positive or negative. We don't know. We do know that this guy is going to be positive, but we don't know whether tangent's going to be positive. But I think we can take care of that in how we set this up. So if theta is positive, then we know that sine of theta is x over 1. And this will be the square root of 1 minus x squared. So notice that tangent is going to be this. So if x is negative, this also still becomes negative. So it doesn't matter which way we draw our triangle, it'll still work out, which is good. We get the natural log of the absolute value of secant, which is 1 over cosine. Cosine is that. 1 over will be switched. 1 over square root of 1 minus x squared, like so. Plus tangent. Tangent is going to be opposite over adjacent. X, so they're both over adjacent. Just like so. Wait, was this actually the sub? No, the sub is 8 sine. Yeah, I was thinking this looked a little weird. This is 8, so it's x over 8. So this is an 8 right here, which means that this is an 8. And this is a 64. Great. And is everything else updated? Yeah, I think so. All right, so then we're going to get 1/8 natural log of the absolute value 8 plus x over the square root of 64 minus x squared, like so. And that's not our final answer, because when x is equal to 0, y is equal to 3. So what is c? What is our constant right here? Oh, this is all going to be positive always. Oh, no, it's not. Natural log of... Oh, never mind. Hold on. An x is 0. This is 8 over the square root of 64. It's just... Oh, look at this. That's 8 over 8. Natural log of 1. Natural log of 1 is 0. So c is just 3. So y is going to be 1/8 natural log absolute 8 plus x over the square root of 64 minus x squared plus 3. And you can really see this domain restriction that we did pop up in this formation of our integral, right? And actually specifically x can't equal -8 either. It's not a perfect domain restriction. Oh yeah. Because x can't equal 8. So these should have been parentheses. But again, there's a way to do this with inverse hyperbolic tangent as well. And then you can kind of see a little bit more of what's going on here, but kind of interesting. Good to do anyway. I took out some of the inverse problems from the homework, or the hyperbolic trig functions from some of these, but apparently I missed this one. But we can still keep it in. It's still a way to do it. Have to make a little assumption. Let me know if you have any questions. Good luck. And I'm sure they probably have inverse hyperbolic tangent in the answer here. But it should be good to go. Bye-bye.